Well, since many of us had an issue with, actually my issue with trying to get the screen to show while I was teaching this morning, I wanted to do a quick overview of some of the major things that we covered during our class time this morning, just because I know people had questions about the notes and different things, being able to write it down based upon what we covered. And I think I resolved our issue, and we should have the ability to view the screen, whether you're online or in person, and I'm looking forward to that on Wednesday. Now, before we kind of move forward with that, I want to make sure we feel a little bit more comfortable with some of the topics that we covered during our class time today. We talked about an overview of kinetics and talking about like why do we care about it, like what are some information that we have. And that was some of the things here related to like how fast reactions happen, what causes reactions to happen quickly or slowly. And now that we have that kind of idea in mind, what we want to do is we want to consider what are some ways that we describe these reactions. And we started by discussing when a reaction occurs, for that reaction to occur, for us to actually go from reactants to products, they need to collide with enough kinetic energy to break those bonds and start forming new bonds. And we proposed some ideas during class that something like an increase in temperature is going to lead to an increase in our reaction rate. And that's because, right, we have these kind of faster and higher kinetic energy molecules, and so they're going to collide with a little bit more kinetic energy. We also kind of came up with this idea that an increase in concentration or pressure, if we're thinking about partial pressures of gases, is going to also lead to an increase in reaction rate, and that's because they're going to have more abilities to collide with each other. It's just more statistically likely for that to happen. We also threw in this idea of a catalyst influencing the reaction rate. So adding a catalyst is going to change our reaction rate. And then we also added in this idea that the identity of our reactants are going to influence their ability to collide with enough kinetic energy and the right orientation to make this reaction happen. So we see there's kind of these four variables. This variable here and this one here really has to do with the fact that we kind of change what the reaction is. We add a catalyst, it's going to influence what the reaction is, the pathway that goes. Whereas temperature and concentration, those are things that we can change without really changing what our reaction is. Now, as we do that, these variables, we want to think, how do we quantitate that effect on these reactions? And that's describing reaction rates. And again, that's either the rate with respect to a reactant or product. So for example, the change in concentration of N2O5 over a change in time. And we'll discuss that with the example that we have, or an overall reaction rate. And this is not with respect to any reactant or product, but it's kind of treating the whole reaction as a single unit as it kind of cycles through. How many moles do we get rid of N2O5, NO2, O2, like the example that we did during our class time. Now I want to go ahead and jump to that example and see how do we kind of take this information that we had. So we have this reaction here where we got 2 moles of N2O5 going away to form 4 moles of NO2 and 1 mole of oxygen. Some information that we had provided to us was that we have 1 molarity of N2O5 initially. After 20 seconds, so that would be our change in time, is 20 seconds. We have an initial concentration of N2O5, and that little 0 there just represents that's the initial amount. And after that 20 seconds, we now have a concentration of 0.2. So now the concentration of N2O5 at some time, we'll just go ahead and put a subscript there to represent that it's at 20 seconds, is now 0.2 molarity, right? So our concentration decreases, makes sense. It's a reactant should decrease in concentration, our products increase in concentration. And so we want to answer the question, what is the rate with respect to N2O5 over these 20 seconds? So the average rate. So that would be the change in concentration of N2O5 divided by the change in time. We ended at 20, our 0.20 molarity. We started at 1 molarity, so it's always final minus initial, and that happened over a time of 20 seconds. And so we would see here we get a change in concentration over time of negative 0.04 molarity N2O5 per second. So our N2O5 concentration is decreasing. That's why we indicate that it's a negative. We will observe that for all reactants their change in concentration over time is negative. It decreases in concentration as our reaction proceeds. And that's every second on average, we lost that much. Now we want to relate this to NO2. So instead of saying with respect to NO2, N2O5, we want to look at it with respect to NO2. Now, we don't have any data or information about NO2, but we do have information about how N2O5 changes. So if we look at this, we're going to see that effectively, that should be twice as fast, right? Because for every 2 moles we get rid of N2O5, we produce 4 moles of NO2. And that mole ratio would be, right, 4 to 2 or 2 to 1. And we want to be able to express this for our reaction. So we're going to go ahead and start with that there of negative 0.04 molarity N2O5 per second. And then what we need to do is we need to convert this to NO2. And the mole ratio here would be 2 moles of N2O5 for every 4 moles of NO2. Now again, we're trying to indicate whether the concentration is increasing or decreasing over time, right? That's this extra piece that we're talking about rather than just reactants going away to form products like we've done, which is basic stoichiometry. And so what we do is we're going to say, for my reactant, I'm going to put a negative value for that reactant to show that the concentration is decreasing. And then I'm going to put a positive value for anything that is a product, because over time it's going to have an increase in concentration over time. And that helps us indicate, as now we go ahead and calculate this, we're going to get a value of positive 0.08 molarity NO2 per second. And so we see it's twice as fast, but it's also positive, right? Because we're producing it as our reaction is occurring. And that gives us our rate with respect to NO2. And we notice this is positive because it's a product. Finally, we want to look at the rate, not with respect to any one of them, but the reaction rate. So it doesn't say with respect to NO2 or O2 or N2O5. So we can go ahead and we can start with what we already know. We could either use this value up here, or we can use this one here. Let's just use the one that we just calculated for NO2. So we have a rate of 0.08 molarity NO2 per second. And we want to convert this to quote unquote like our moles of our reaction. So for every 1 mole of reaction or 1 unit of this reaction, I'm going to produce 4 moles of NO2. And that's kind of the ratio that we have the ability to relate to each other, to say every time that that reaction cycles through, I'm going to produce 4 moles of NO2, get rid of 2 moles of N2O5, produce 1 mole of O2, and we would get a rate of 0.02 molarity per second. And note, we don't have anything here saying with respect to NO2 or O2 or N2O5. It's just saying for the overall reaction. And we also note that that is a positive value. So now we have the ability to describe the rate with respect to a reactant or a product or the overall reaction as we went through in this example during our class time. Now then what we did is we went ahead and we took that information and we went and we translated that to an example where we actually completed these reactions. So what we did is we took this kind of 2-step reaction that we had where we have these kind of colorless solutions that we have, and we had iodide react with hydrogen peroxide, and then we have some sulfuric acid to make it acidic, produces this I3 minus ion, and then what we notice is that that I3 minus ion is then reacted in our second step. And then we go ahead and we produce I minus, but then we notice our I minus then has the ability to continue to react. So the net change is that our concentration of our iodide ions is not really changing, but because we get rid of 3 moles and we produce 3 moles in this overall reaction. So if we were to look at our overall reaction here, kind of like we did with Hess's law, we see that those are on opposite sides of our reaction, so is our I3 minus. And we're going to have an overall reaction of our hydrogen peroxide, a couple of protons or hydrogen ions, our S2O3 2 minus, producing 2 moles of water, and our S4O6 2 minus. And so we have this overall reaction that's occurring. And what we're trying to do is express how fast does this reaction happen. The way that we indicated that our reaction was done was that at some point we ran out of our limiting reactant. And we could go ahead and identify that based upon the molar amounts that we have of each of these, but we see that our S2O3 is our limiting reactant. And that would mean once that's gone, now any I3- I produce no longer gets consumed by that. And it's going to go ahead and attach to this starch molecule and make this really deep blue, purple colored solution from that starch binding to our I3-. Now that we have that, what we notice is that we then went ahead and did this reaction multiple times. We have this data here, and I'll go ahead and share our data sheet afterwards so you can go ahead and view it if you didn't get a chance to copy it during our class time. But what we wanted to do is, if we think of how would I calculate the average rate with respect to S2O3, our concentration of S2O3 goes from 0.0028 to 0, and that's 0 at the point where we see the color change, because the color change means we've gotten rid of all of that limiting reactant. So for example, if I want to calculate my average rate here, I want to look at the change of S2O3 over the change in time. We end at 0 molarity. We started at 0.0028. And then we went ahead and we see, well, then I would divide that by my change in time here, which would be 27.2 seconds. And we would find that our reaction rate here is 1.03 times 10 to the negative fourth molarity S2O3 per second. And so that's what we would have for our reaction rate here, negative 1.03 times 10 to the negative fourth molarity per second of S2O3. We can then continue that on for all of these reactions here and fill in the rest of that table. But then we can go ahead and just like we did using our mole ratios with NO2, N2O5, and O2, we then have the ability to look at corresponding that to our overall reaction rate, which is basically 1 to 2, right? We have 2 moles of S2O3, 1 mole of the reaction, and that would give us a reaction rate of 5.15 times 10 to the negative fifth. From that, we were able to conclude a couple things. Number one, that as we go down here, we see that we decrease the concentration of I-, which we have here with our potassium iodide, and that leads to a decrease in our rate. And we see here, that's something we propose, saying concentration is going to influence the rate. It decreased the concentration, we see a decrease in the rate. Additionally, as we compare these 3 here, we notice that an increase in concentration of H2O2, our hydrogen peroxide, leads to an increase in our rate. So between these 3 here, we see an increase in our hydrogen peroxide concentration leads to an increase in the rate that we would observe for our reaction. And then we also saw, comparing our temperatures, we noticed that a decrease in temperature led to a decrease in our reaction rate. And we propose that as well because they're moving slower, they have less kinetic energy, and that leads to a slower reaction rate. And we were able to observe that when we compare these 2 here, that decrease in temperature leads to that decrease in rate. Those were kind of the expanded out in these questions here of 3, 4, 5, and 6. And then we're going to, at the beginning of class on Wednesday, we'll jump into kind of the application of this and thinking about what about S2O3, what about H+ ions? Will they influence our reaction rate? And we're going to go ahead at the end of all of that, use our data to be able to describe our rate law expression. And that's where we ended class on Monday, of thinking about how are we going to get to our rate law expression and what is it going to tell us quantitatively about our reaction. So I hope that helps give us a little bit of a wrap up of what we maybe saw or missed during our class time online today. But I look forward to another wonderful class time on Wednesday. If you have questions, please feel free to reach out to me. And I will see you either in person or online on Wednesday.